All right. Why don't we get started? Okay. So today we're going to talk about if about learning, the feasibility of learning, and that corresponds to one of the natural trade-offs that I alluded to in last Thursday's and Tuesday's modules about the trade-off between uh, error and the amount of data and model complexity. So hopefully we can get through the entire module. If not, then we can just finish the balance of it on Thursday. And so the reading is from Learning from Data. Hopefully you have the textbook. And there's also, this corresponds, there's the MOOC YouTube video, and I'll certainly post the screencast for this hopefully tonight. It takes me about 2.5 hours between the editing and the rendering and the uploading to do so. And I do that for my 3 classes, so that's a little bit of time. All right, so last time, to jar your memory, we talked about the anatomy of a learner, and we described the components of it, and we started with the unknown target function. It's hidden from you, and therefore you do not have control over it. And we talked about the target function as being a function whose domain is the set of all data inputs that you can have, and the range, or the association between an input from the domain ascribed by the associated with the target function, is a set of labels, and the class labels that we're assuming are so-called binary decision problems where you have a +1, -1 labeling. And we also said that if you only have a binary problem, your +1, -1, or your binary labels, you can certainly synthesize a k-way classification by just aggregating those +1, -1s in the right way. And we can certainly talk about that a little bit. And so this unknown target function, it's out there, but you don't know what it is. And it's merrily going along and associating class labels ground truth, with each of the feature vector instantiations that are given to you. And so from that, we described rather our label instance pairs, where our instances are vector valued in d dimensions. So we have x1, x2, x3, up through and including xn. And the example we gave for that was the credit approval problem, where each of those d-dimensional x vectors in the credit approval problem would represent each of the features that collectively describe one of our historical customer records, things that you would get from a loan application, things like the number of years in residence, annual salary, and things like that. And so associated with each data input in D dimensions, we have the associated ground truth class label assigned by the target function. And so corresponding to customer number X1, we would have the corresponding Y1, which in the credit approval problem would be +1, representing somebody who was approved for credit, and -1 would be the label associated with someone who was denied credit. And so these would be our historical records that some lending institution might have. And we said in the anatomy of a learner that both the target function and the training examples are given to you. You have no control over them. So then we talked about the other components of our anatomy in the anatomy of a learner. We talked about this hypothesis set. And this hypothesis set, as we said, is nothing more than a set of candidate formulas. And the example I gave was, imagine the set of degree 10 polynomials. There are a large number of degree 10 polynomials that you can form, both by setting the real valued coefficients for all of the terms in that degree 10 polynomial, including whether that coefficient is 0 or non-zero. And because you can set those coefficients to 0, inside of the set of degree 10 polynomials is included the degree 1 polynomials, degree 2 polynomials, degree 3 polynomials, and so forth. And so the goal then is to find a hypothesis within this set of hypotheses, and is done by searching in some fashion for a given working hypothesis, little h, that mimics as closely as possible the ground truth labeling by the target function. And so you start out describing your hypothesis as a set of weights, W, and you search for one set of W because a unique setting for the weights corresponding to a particular working hypothesis is is used to label or output a label associated with each one of the data inputs. And so that hypothesis either agrees with or does not agree with the labeling of the ground truth target function. And now the problem boils down into a search for that hypothesis within the set of working hypotheses, ultimately resulting in a final hypothesis, which is the best hypothesis as deemed by the one that most closely approximates the labeling decision by that unknown ground truth target function. Any questions about this? Does that make sense? And so what does that search? That's the role played by the learning algorithm, A. And this learning algorithm's job is to search in some fashion through the space of hypotheses for that best hypothesis when it halts the final best hypothesis, which is the learned approval formula. And we also said that together, the hypothesis and the learning algorithm, it has a name. It's called your learning model. Okay? All right. So let's continue on. And again, the whole goal, what we'll learn today, is this idea of out of sample performance. So what does that mean? All right, so we have our historical data. So we have our records that we might have from the lending institution. And this would be all that information from the mortgage, I keep saying mortgage, from the loan application for each of our applicants. And of course, the ground truth label is assigned to these records, each record corresponding to a single user or customer who has applied for mortgage, and it has assigned a label. And so it's going to give some actual output, whether someone was a good credit risk or bad credit risk. Good meaning +1, a so-called positive example, as you'll sometimes read in the literature, or a negative example, hence the +1, -1 labelings in the binary decision problem. And so you have a hypothesis, and your algorithm will search through the space of hypotheses from your hypothesis set, ending in some final best hypothesis we're calling G, and we'll use that notation throughout the course of the semester. And the goal then is so that when you're given a new record, say a new customer comes in to the lending institution, he or she fills out an application, and this new record does not exist anywhere within the historical data, right? It's brand new to your learning algorithm. And so what the goal then is for your final best hypothesis, when it outputs a class label, for that class label to be correct for that new data. And so one of the measures that we're concerned about, and that's the quality measure that we're going to carry forward throughout the course of the semester, the quality measure for what a good final best hypothesis is, it's one that performs so-called out of sample, right? And so we'll kind of define and solidify what that word out of sample performance means. And so at this juncture, we'll just say in sample, this is the data that you've seen, right? And you use that to find your best hypothesis, but you want to find it in a way, or search through your set of hypotheses in a way, so that it performs well out of sample on new data that your model has not yet seen. So that's going to be our goal, and there are all sorts of nuanced issues and natural competing forces that we'll see and study along the way. Okay? All right, questions? All right, so let's go forward. And the question then, I hope I have the right slide deck. Yes, I do. Okay. All right. I wasn't expecting this slide. So now I remember. So the question of whether or not we can really learn, recall that we had some assumptions that we're working with. We said that the target function was unknown, right? And you also have data, right? Without any data, there's nothing that you can learn. And the important nuance was that this problem is such that you can't know what the function is, and it's not easy to guess. Because if you know precisely in closed form what the target function is, just implement it, right? You don't need learning, right? Also, a pattern must exist. There must be some relationship between the values that describe the data items, your features, and the output label, right? There has to be a relationship. If there's no relationship, you also can't learn. A pattern must exist. And so what we're asking here when we ask the question, can you learn, right? Is it feasible? Is the question of whether or not a function, how it performs, what it does outside of the data set that you're given, right? Now, mind you, you don't have control over the data set you're given, your label instance pairs, your historical data. And so if the target function is truly unknown, you could assign any values you want out of sample, outside of those data points you've seen. But it's a little bit different from that, right? And so when we saw the perceptron, there are certain operating assumptions for the perceptron. Perceptrons work well or work best if your problem is linearly separable. And it makes the assumption that you can linearly separate your data points. So you can use a linear model, a weighted sum in some number of dimensions, whether it's a plane, a line on the plane, or a hyperplane in more than 2 dimensions. If you can separate your positive instances from your negative instances with a hyperplane, then perceptrons work well. Now, if your data is not linearly separable, there are some tools you have. You can transform the geometry of the data to so-called linearize your data. But the perceptron, even in the absence of linearly separable data, it'll try its best, but it's going to make a lot of mistakes, right? So there are certain assumptions we can make, but the question of whether or not you can really learn on a data problem is really a question of focus on how this particular final best hypothesis works outside of the samples you have, i.e. on brand new data. Okay, so we're going to carry through a bounding approximation called Hoeffding's inequality, but how this is motivated is using a balls and bins approximation. So what we'll do first is we'll carry the analogy to show what the bounding approximation is, and then we'll relate this to the anatomy of a learner, and then use that for something that looks like a learning algorithm to search for the final best hypothesis. Okay? All right. So here we have a bin. And this bin has marbles in it. And there are 2 types of marbles. There are red marbles and there are green marbles. Now, of course, some proportion of the marbles in this bin are red and some proportion of the marbles in this bin are green. Now, obviously, in order to show you what is in this bin and to describe it, I have to show you a cutaway view of the bin and you can actually see the proportion. But in truth, imagine this bin was kind of like pottery or something opaque where you couldn't really see what's inside. All you can do is reach inside, pick out a marble, note down the color, replace it. Pick another marble, note down the color, and replace it. And so therefore, in that scheme, you're not really preferring one marble over another, right? Bless you. So the marble will kind of, you drop it back in, it gets mixed in with the other marbles. You could choose the same marble again with some probability. You could choose a different marble. 2 people could pick 10 marbles or some number of marbles and many marbles, record the color, put it back, and both get different selections, right? So let's define a parameter mu, and mu is going to be the percentage or the proportion or probability of the marbles that are going to be red inside of the bin, right? So if 10% of those marbles were red, then mu would be 0.1, right? Now, if the probability of picking a red marble is mu, well, by law of total probability, the probability of picking a green marble, if there are only red and green marbles, is just going to be 1 minus mu. Okay, that's just simple probability based on the Kolmogorov axioms. And so we're going to pick this marble, and when we pick a marble out and record its color and place it back into the bin, we're going to write down the color that we picked, right? And that's going to be our sample, right? So we have out of sample, which are the marbles, ground truth proportions that are in the bin, and you don't really have access to that proportion, but you know it's there, right? And then we have in sample those colors that you're going to sample. Now, certainly, oh yeah, I forgot that part. In sample. So when you pick a marble and you write down its color, you do it some number of times n. It doesn't matter what n is. N could be large, n could be small, n could be 10, n could be 1,000,000, but n is going to be the size of the sample for marbles that you pick, write down, and put back into the bin. Alternatively, you can imagine this bin had an infinite number of marbles. And in that case, if it has an infinite number of marbles in it, you're going to pick a marble and keep it, right? And you write down or keep it and you just kind of line it up. So either it's infinite or you look at the color, write it down, and replace it. It's the same problem as far as our consideration is concerned. So you take your sample, you sample from the marbles inside the bin, writing down the colors and replacing the marble back to the bin. And the other parameter, nu, right, kind of looks like a squiggly V, Greek letter nu, that's going to represent the fraction of red marbles that you count, or proportion of red marbles in your sample, right? So mu is ground truth, the proportion of red marbles in the bin, and nu, with an N, is going to be the proportion of red marbles that are in your sample. Does that make sense? Okay, so essentially, when you pick a marble, when you produce a sample from this bin, you're basically communicating something about mu, the probability of red marble's ground truth, that you don't have access to, right? I'm just drawing it on the board to describe the scenario. It's communicating something, mu is communicating something about itself through these samples, right? Okay, so that means there should be some relationship between mu and between nu, right? So we're going to carry through this idea of this communication and what that relationship might be, and some of the nuances associated with the relationship between the bin proportion, ground truth, mu, and the sample proportion of red marbles, nu. Okay? All right. So let's take a look. So then the question is, well, there's some relationship, and they do communicate. Nu communicates something to mu. Mu communicates something to nu. And so the question is, does nu, which is the sample proportion, you know what that is? You took the sample, you can look at it, you can count it, you can compute that proportion. Does what you know, nu, tell you anything about what you don't know, mu? So what do you think? Does it tell you something about it? Yes? No? Not a trick question. Well, it kind of is a trick question. Yes, yes, it does. It does. But there are conditions. You're absolutely right. Yes. But there are conditions where it doesn't tell you much, where nu doesn't tell you much about mu, right? So let's take a look at this. So when yes and when no. Well, this has to do with what is probable versus what is possible. And I'll explain what I mean about this. So you can construct or think of pathological examples where, for example, the sample can be mostly green. So nu is going to be very small. So let's say these are mostly green or all green, but yet the bin was mostly red, right? So you could just be so unfortunate. Let's say, only 10% of these were green, right? Ground truth. So let's say it was 90% red and 10% green. You could have a pathological example where you pick samples, and for whatever reason, your sample happens to select mostly green because you're only taking from that green portion of this bin. That can absolutely happen. Now, will that happen a lot? Probably not, all things being equal. But it could also happen if your sample size is not big, quote unquote, enough, right? And that's another issue. How big is big enough? Because, for example, you could have 90% red and 10% green in the bin. And if your sample size is only 3, you could just pick green, green, green the first 3 times and say, okay, it's all green, right? And that's not correct. You could pick 100 marbles as your sample, and in a very, very rare circumstance, if you did it enough times, you get one case where you're going to get mostly green, even though you picked 100. So is it possible? Absolutely. But then the key consideration here is how often is that going to occur? So what is possible is not the same as what is probable. So that means in the learning problem, we need to think about what is possible and what is probable when we think about the relationship between nu, in sample, and mu, which is out of sample. Now, of course, when you think about in sample, out of sample, and you hear those words, naturally, because it's in the bin, you want to say in sample is in the bin, right? But in the bin is out of sample. The sample that you obtain out of it, that's in sample. Okay? All right. So let's carry forward these ideas about what is possible and what is probable, because here we've just talked about an example where absolutely you can have mostly green sample even though the bin is mostly red, and vice versa. There are absolutely cases where you can do that. In some of those cases, it might be that the sample is too small, all right, to truly represent what's happening. So it's, in essence, you can think that mu is not communicating enough for the representation of nu to be correct, right? Um, Other cases, it's this very unlikely event where you were just unlucky, right? You just happened to choose 100 marbles and they were all green, even though 90% of them in the bin were red. That can absolutely happen. So there are two pathological cases that do impact your learning. And so this has to do with what is possible, it can happen, versus what is probable. How likely is that to occur? Because certainly if you do something enough, eventually something that's unlikely may show up. Okay? All right. Does that make sense? So let's carry this a little bit forward. So if I make the number of samples n, the size of our in-sample points, large as n approaches infinity, then nu implies mu. But why? Why is this the case? Right? Certainly the law of large numbers has to do with it, but think of a presidential poll, right? So let's say, you're electing an elected official and you're not actually running the election, but you're calling people beforehand to say, hey, which candidate do you want to vote for, right? So if you only called 100 people, that might not be as accurate. And those 100 people you call, if you tried to make it equal, you'd only call 2 people from, say, in the US out of each of the 50 states. That's not very representative because every state has all sorts of regions where people have different ideas about how their elected official should, what their belief system should be. And it's very likely that you're not going to represent all of the different ways people think in an area, right? And so certainly as you make n larger, you have more of an opportunity to know associated with each data point, and if you think of each marble as a data point, right, then you have more opportunities to see all the different possibilities that can occur, right, and get better representation across a broader range of possibilities that might be encountered, right? So as n approaches infinity, i.e. your sample size increases, then your nu, which is your out of sample proportion, I'm sorry, your sample, your in sample proportion, I naturally start to flip that because I want to so badly say inside of the bin is in sample. So let me start over. As n approaches infinity, or your sample size gets large, your in sample proportion starts to look a lot like or implies your out of sample proportion, and your out of sample proportion mu is the ground truth, but you just don't have access to it. Does that make sense? Okay. So the target function, when you talk about a labeling, it has an opportunity to tell you the output corresponding to every single input. Because if n is exactly equal to infinity, right, when you sample an infinite number of samples, you're basically saying, target function, show me what you would do on everything that is possible to label, right? So that's the perfect situation. And so therefore, as n gets bigger and bigger and bigger, you're giving the target function an opportunity to communicate more and more and more about how it would label various types of values that these feature vectors can take on. Okay? So that's why this occurs. The in-sample nu starts to approach out-of-sample mu. Okay? All right. So for large sample size n, we say that nu approaches mu. And we could also say it differently and say that nu gets really, really close to mu, right? Literally, they start to get closer and closer and closer and closer and closer to one another. Now, mathematically, how might we write that? We could say that nu and mu, as they get closer, they're within some error tolerance, some epsilon ball, and we'll call that difference epsilon, right? So we say that as n goes to infinity, well, the difference between nu and mu is less than that epsilon, that error tolerance. So we're going to introduce a little bit more notation, and then we're going to get to this probabilistic bound that we're going to use to talk about the relationship between complexity, error, and the sample size. Okay? So probabilistically, what is it that we want? What we want is we want good out-of-sample performance. We want our models to perform well on data that it has not yet seen, right? Performance out of sample. So if that's the case, then in terms of this proportion from the bin example, we want our proportion associated with the in-sample points, our new, to be close to, mathematically, or within some error tolerance, close to mu, right? And so if that's the case, we want to probabilistically, because it's based on probability, well, as I said, it's what is possible versus what is probable. And it's the what is probable gross level behavior that we're concerned about. We want to say most of the time, i.e. probabilistically, nu and mu are going to be very close to one another within some epsilon tolerance. So how we express that is we want to say the probability of a bad event happening is small. And what that bad event refers to is that mu and nu diverge from one another, i.e. that the difference between them is greater than that epsilon tolerance. So something bad happening is small. We could say the probability of that undesired event is going to be at most or less than equal to some quantity, right? Okay, does that make sense? All right, so let's further develop this idea. And how we express this idea of bad thing happening, well, we use absolute value of the difference between nu and mu, okay? As we don't care which one is greater, what we care is the magnitude of that difference, right? So we're going to use the L1 norm here. And so we say that bad event is the probability that nu tracks with mu by within some error tolerance epsilon. So the absolute value of nu minus mu exceeds or violates that epsilon tolerance is going to be less than equal to some probability. Okay? Does that make sense? Okay. So let's carry this even further. So now, this is based on something called the law of large numbers. And depending on a whole bunch of stuff, I may or may not include the proof. But for now, you're just going to have to take it on faith that this does hold true, right? It's a uniform bound, and it's expressed as an exponential, decaying exponential, which is good news, which means that it's going to get smaller and smaller and smaller. It's not a super hard proof, but it's a complicated proof. So we might or might not include it depending on how the schedule goes, okay? But it's absolutely there. It's called Hoeffding's inequality, and it's based on the law of large numbers. It's a standard proof in statistics. Okay, so the good news is that the probability that nu is close to mu within some error tolerance epsilon is going to be at most e to some decaying negative exponential, right? And that negative exponential is parameterized in terms of the number of samples that you have, the sample size. We just got done saying that if you have more samples, you have more opportunity to know how the target function would make an assignment. And in doing so, right, you can explore more of the different feature values within that bin and get a better representation, all things being equal. Does that make sense? And so certainly this negative exponential, where e is exponentiated to the negative n, where n is the sample size, it sort of has that quality, right? As the sample size gets bigger, the probability that nu and mu are going to be far apart gets smaller and smaller and smaller. Okay, so the probability of being outside a specific error tolerance gets smaller as you have more samples. That's the good news, right? But the bad news is that the error tolerance matters, right? If you want nu and mu to be very close to one another, you're going to make your epsilon error tolerance really, really small. If you want nu and mu to be more generous in terms of the tolerance, maybe you want them to be further away, then this epsilon might be something like 0.5 or 0.9. If you want them very close to one another, you might have 0.00001, right? And how the tolerance fits in with this is as follows. So here we include an epsilon squared term in the exponent. And so what that effectively does is it dampens the effect of the sample size. And so if you want a very close tolerance between our out-of-sample nu and our in-sample ground truth mu, well, how you pay for that tolerance is in terms of the amount of data that you need. So what does it do? Well, we have our epsilon squared term, and if epsilon is relatively large, like 0.9 or zero point 0.5 or zero point 0.1 even, well, you need a decent number of samples to make sure that what is probable, i.e. the bound on this probability, is relatively small. Okay, that's kind of nice because epsilon squared is polynomial, so you kind of need, not that many samples to overcome that dampening, so that the right-hand side of this inequality is very small, putting that bound on the probability. Now, if epsilon is really, really, really small, like 0.0000, like 10 to the minus 6, right? Now, what happens if you square 10 to the minus 6? That's 10 to the minus 12. And what that means is that you need a phenomenally much larger number of samples to overcome that tolerance. And you can think of it sort of, a little bit like physics, right? If you want nu and mu to be really, really close to one another, almost the same, well, that means your tolerance is very, very small. But you don't get that for free. How you pay for that is by having a larger number of samples. If you only have a fixed number of samples and you can't afford any more, well, what breaks is you have to loosen up the tolerance to pay for that. And so what does this mean? It means that, well, I know nu and mu, when you choose the right samples and you choose the right tolerance, you can guarantee that while you don't know what mu is, you can calculate nu and then guarantee, if you choose your other parameters, the sample size and the tolerance right, that the ground truth, you don't know what it is, but it's not that far away from you. Okay? And it's not that far away from a quantity that you can calculate, that you do know. Does that make sense? Okay. Any questions about this? All right. So you might be asking, well, what in the world does this have to do with learning and algorithms and hypotheses? We're going to relate those two together, but first we want to give the expression for Hoeffding's inequality and explain the trade-offs before I map it to the learning problem. Okay? All right. So this is the full Hoeffding's inequality, and if you look through the proof, it actually talks about two hypotheses, which is where the twos come from, and this is what Hoeffding's inequality is. But again, we won't prove that, at least at this juncture, and depending on schedule, maybe we'll do it, maybe we won't, because we need to talk about other aspects of the linear model before we can introduce the full proof. So for now, just accept this expression as true, and this is Hoeffding's inequality, and it says the probability that your in-sample performance is different from your out-of-sample performance by more than some error tolerance epsilon is at most or no bigger than 2 times e to the minus 2 tolerance squared times the sample size, right? Okay. Now, this idea of having nu and mu coincide goes back to a framework, a complexity framework for learning called the PAC learning framework. And PAC stands for probably, approximately, correct, right? And so the probably part corresponds to the fact that here we have a probabilistic bound. This is a probability. And the special thing about this probability, right, your probability is no bigger than that, but this expression for that worst case probability does not involve any unknowns. It does not involve mu, right, which is kind of nice. It's uniform, and it's the worst case. And in that worst case, you know that your model performance can either be that or it can be better than that. Okay? And so that's where the probably comes from, that it's a probabilistic bound, and that talks about what is probable, right? Now, approximately talks about this epsilon, the error tolerance. And it says, what is the closeness relationship between our in-sample nu and our out-of-sample mu? So you might not know what mu is ground truth, and you don't, it's hidden from you. But if you choose the conditions for your learner correctly, then using your in-sample nu, you know that your ground truth is not that far away from you. Okay? All right. So this is called the PAC learning framework. It stands for probably, approximately, correct. And what that really corresponds to, if you want to use more casual language to describe it, is that nu and mu are close to one another some of the time or much of the time. And really what you want is much of the time they're close to one another. Does that make sense? Okay. So the PAC learning expression is expressed through Hoeffding's inequality, and it's valid for positive n, positive integers, and also for epsilon, tolerance is greater than 0, right? It's not asymptotic, but it holds for such values where you create these quote unquote good conditions. And it's based on the law of large numbers, which is a standard statistics um, identity that you use in various sort of proofs. Okay. Any questions about this? Does that make sense? Yeah. All right. So let's move on. And what Hoeffding's inequality gives us is that we have a trade-off between the sample size n and the error tolerance, i.e. the closeness you desire between your in-sample and your out-of-sample performance. And so you need more samples necessarily. You need more samples if in order to pay for stricter tolerance. The more you want in-sample and out-of-sample performance to coincide with one another, in practical terms, if you have your in-sample performance, which you can know and can measure, and you want to make sure your out-of-sample performance is very close to what you're doing, you need a lot of samples to do that, right? And so the samples are how you pay for a stricter tolerance. Now, in practical terms, in a real machine learning task, well, what if you can't go out and get samples easily? Well, you're going to have to relax your error tolerance. You can't expect out-of-sample performance to be very good. But if it's very cheap and very inexpensive, not necessarily in terms of cost, but in terms of feasibility, for example, you're doing a computer vision application, you put up another camera and turn it on, it gives you 60 frames a second, right? That's easy, right? So you have much abundant data and it's easy to get that data, then absolutely you can pay for stricter tolerance, right? And so in practical terms, when you have a machine learning problem, it's not to say this learner is better and this learner is worse. It's about what are the conditions and can you create the right conditions so that you can guarantee that if you have a certain in-sample performance on the data that you have that you use to train your models, can you guarantee that out of sample it's going to be so different within a certain bound, okay? Within this error tolerance. Okay, and so what this says is that nu is close to mu implies that mu is close to nu. So what does that mean? So when you're sampling, absolutely, the ground truth proportion mu is going to dictate the proportion that you measure over your sample nu, right? That's how it works because mu is the one that governs the data itself associated with some probability, and nu is what you measure, right? But you're kind of flipping it in machine learning. You're saying, okay, well, I know that mu governs nu, but what I'm going to do is I'm going to focus on what I can calculate, what I actually know. I actually know what nu is because I compute some samples and I calculate my proportion of red marbles, right? So what I do is I say, okay, well, I'll never know what mu is, the ground truth. I can calculate nu, but I'll use this relationship that binds how far away nu and mu are to say, okay, well, I'm going to focus on what I know and use that distance bound, right, about how far away ground truth is to tell me something about ground truth. And I know if I get a certain performance on my historical data, then out of sample, my performance will be no worse than this plus or minus some delta. Does that make sense? Okay. Any questions about this? No? No questions? Okay. So nu is close to mu. I know nu, and now nu tends to be close to mu. You're kind of taking what you know and using that relationship to bound how good your performance will be out of sample. Because at the end of the day, what you're concerned about is your performance on new examples that you have not yet seen, new marbles from the bin. Okay? All right. So let's take a look at this multiple hypothesis example. And now we're going to start to draw connections between the single bin case and other aspects of the anatomy of the learner to kind of round out this example. All right, so each bin, as we said, has an associated value mu. And as we said at the outset, mu governs the proportion of marbles in this bin that are red. Now, in the slides, I think I had a typo here. I said g of x equals f of x. I meant to say h of x equals f of x and h of x not equal to f of x. I just caught that before class and I'll update it on the blackboard. But for now, you can just assume this should be h of x and not g of x. G of x is the final best hypothesis. H of x is the working hypothesis. So here we have mu, which is the ground truth proportion of marbles in the bin, which are red, right? Now, we don't know what it is, but it's there and it's governing the proportion of marbles that are red. And so we have a target function, and that target function's job is to input data points, x, so they're d-dimensional vectors, the credit information, the application for each applicant for credit, and it's going to associate it with a ground truth class label, y, which is +1 for good credit risks, -1 for bad credit risks. So we don't know this ground truth target function. Each marble represents a data item. So represents the vector of values and instantiation of that vector in d dimensions corresponding to all of the applicant information for a single applicant. So now we're going to make some connection between this problem that we're talking about that was governed by Hoeffding's inequality. Now we're going to connect this more directly to the anatomy of a learner. So let's assume, yes, the marbles, they represent data vectors, each of which corresponds to a single applicant. And we know that the ground truth target function, which is unknown, assigns labels. So inside of the bin, a marble is colored red if the current working hypothesis, h of x, does not agree in its labeling of that input feature vector, does not agree, h of x does not agree with the ground truth target function. So for example, this red marble, you might say an applicant with a certain number of years in residence and a certain salary is labeled as a bad credit risk by the target function, but the hypothesis h of x says that's a good credit risk, right? They disagree. So we label marbles red if the working hypothesis h of x disagrees with the ground truth target function on that data item whose feature vectors are associated with each marble, okay? All right, so now here we have an example, the green marble, h of x agrees with the target function. And of course, for a single hypothesis, how do you form it? You form a single hypothesis by taking the weight vector and setting its value somehow to some instantiation. It could be W1, W2, W3 is 5, 17, and 2.5. It doesn't matter what it is, it's just a single hypothesis h of x. Okay, so for a given bin, certainly for a hypothesis, you're going to have a different assignment of red and green based on the hypothesis. That makes sense? Because if you color red to represent the hypothesis being different in its labeling from the target function, and you color green, meaning that they coincide, what this coloring really represents is a measurement of the coincidence or agreement between a working hypothesis and the ground truth target function. Does that make sense? Okay, good. So now there's that one connection. So let's take a look at some other things. We're not done yet. So you have a specific hypothesis, and for a given hypothesis, you have a certain amount of agreement, green colorings, and you have a certain amount of disagreement, red colorings, for all of the marbles in the bin, where a particular marble represents a particular d-dimensional feature vector for a credit applicant. So given a specific hypothesis H, you can now draw marbles from the bin, and then you see the actual values, the data is given to you, and now you label it for your in-sample performance. So in sample, you can absolutely compare the agreement of your hypothesis, your working hypothesis, with the ground truth target function. That's called error. It's called training error, right? So given a specific hypothesis, H, you draw the marbles, and then you estimate the level of agreement that that hypothesis has with the ground truth target function. So with enough samples, right, you have enough samples, a large enough, and we didn't describe what enough means. Well, we know now enough means a big enough n so that for the given tolerance, that probability in Hoeffding's inequality is small, right? That's the n we need, right? Absolutely. But with enough samples for this specific hypothesis, we know that the in-sample level of agreement and disagreement is going to be a good replacement, or it's going to be close by to the out-of-sample level of agreement and disagreement. Does that make sense? Okay. So this particular case is for a specific hypothesis. If my hypothesis corresponds to weight vector, W1 is 5, W2 is 6, and W3 is 2.5. That's a specific hypothesis. This is not learning. This is verification of a hypothesis. This is measurement of the agreement of a hypothesis with the ground truth target function. Does it say +1 and -1 in the same places as a target function? And so if you're looking at the proportion of red marbles in sample, which is new, that's asking what is the level of disagreement or the error that this hypothesis has with respect to the ground truth target function. Does that make sense? Okay, so this is not learning, this is verification, and it only tells you how good this hypothesis is. Now, in this particular problem, you're not finding a hypothesis. And we said when we talked about the anatomy of a learner, we talked about the learning algorithm's role as searching through the space of hypotheses, looking for the best hypothesis, the one that most closely agrees with the target function. And what that means is that when you sample from this bin, right, the level of agreement and disagreement coincides between the hypothesis and the target function, right? So you're gonna have a lot of green marbles, right? Okay, so you're not finding H here, so we're gonna add this idea of searching for or finding this notion of a best hypothesis. And how you do this, let me check the time, is by visiting more than one hypothesis and comparing the level of agreement and disagreement with the target function. Okay, so we're going to add one more thing. And that thing we're going to add is going to be a probability. And if you look at this bin, right, we have one marble here, we have another marble, we have another marble. And how these individual marbles differ is in the feature vector values that they have. So one person might have a years in residence of 1 year, another might have years in residence of 2 years, another might have years in residence of 10 years, and so forth. So each one of these marbles, if it represents the feature vector in d dimensions of a particular applicant, well, we're going to have some distribution that is responsible for giving you these different feature vector values that you have available or possible in this bin. And so we're going to augment the anatomy of a learner to include a probability distribution. And this probability distribution can be any form. We haven't set any restriction on it. And this probability distribution is going to be the entity out there. And again, you have no control over it, but it's responsible for giving you all of the values you see that comprise your feature vectors for your inputs. And so if you imagine, for example, let's say you have a camera, a computer vision experiment, and you want to measure the jacket color of people that walk into the campus center and the student center. Now, if you're Delaware State University, maybe because of the colors of the school, you're going to see red and Carolina blue and white, right? If you're at UNC, North Carolina, they have blue and white. Right? If you're at a different school that has different school colors, you're going to see a lot more of certain colors for jackets in the campus center that students are wearing. And so this distribution, while it doesn't have any particular prescribed form, it's responsible for giving you the feature values, and in the case of the credit assignment, the particular values that describe your candidates. It gives you all of those values that you can observe among the feature vectors that are given to you. And again, you have no control over this probability. Now, it is a fact that the same probability that gives you the values that you see in your historical data should also be related to, it might be a little different, but it shouldn't be completely different. It should also be related to the values that you're going to see when you get new data out of sample, right? So an example of that is, well, you're at Delaware State University, you put a camera in the campus center, and you measure all the jacket colors of people walking in, and maybe you do this for half a year, maybe you do it for a whole year, right? So it's the same distribution governing jacket color. But where that P would be different in sample versus out of sample is you're at Delaware State University, you collect a lot of data, you use that as your in-sample data points to train your learner, and then out of sample, when you're going to use it to say, aha, there's a jacket, let's say you brought that trained system to UNC, University of North Carolina, and now you used it. So in that case, out of sample, this P is going to be different versus in sample when you had that training data. So one of the requirements of a learner is that this probability that governs the data that you're given that you use in sample to train your models must bear some relationship to the values of data that you get as new data out of sample, right? Because in essence, if it's a different P, that means, let me go back to this example. If it's a different P, that means when you get your sample, it's coming from a different probability distribution and not from the same bin that you use to get your in-sample points, right? And there's a problem with that. Okay, so when you design your learning models, you want to be very clear about the distribution that gives you the in-sample points that you use in your learning algorithm to find your final best hypothesis. Okay, any questions about that? Okay, so let's continue this example forward. I lost my place. There we are. Probability distribution. So we augment this diagram with a probability distribution that is responsible for giving you all the different feature values for all of the points, data points represented as marbles in your bin. Okay. So, and also I forgot to add that this probability distribution, it affects mu. And mu you can think of as the parameter that governs this hidden probability distribution over which you have no control. Okay, so the coloring of the marbles is based on a specific hypothesis, right? And the agreement or disagreement of that hypothesis relative to the ground truth target function. And so you could pick enough samples in sample to show that the hypothesis works well, but it might perform very badly when you give it new marbles from the same bin, right? And why is that? We'll talk about that in a little bit. So if you can select one hypothesis, you can certainly select multiple hypotheses. And if you think about what the learning algorithm is doing, you start out with some weight vector W, that's one hypothesis. You look at the agreement with the ground truth target function. You select a new weight vector based on that existing weight vector, that's selecting another hypothesis. So essentially what happens, mapping this to the learning algorithm, you're searching through multiple hypotheses. You start with H1, and H1 has a certain level of agreement and disagreement with the ground truth target function. So out of sample, corresponding to items in the bin, right, you have a certain level of agreement. So here, this has a lot of disagreement with the ground truth target function. You draw data points, let me not knock this over. You draw data points in sample from this bin, and you measure the level of agreement, nu, of the target function, the first one, H1, our first working hypothesis, with the in-sample points that you sampled from the bin. So then you choose a different hypothesis. Now remember, the agreement and disagreement, it's based on the hypothesis. So if you choose a different hypothesis, you're going to get a different level of agreement and disagreement with the ground truth target function. So you change your weight vector W to form a second hypothesis, H2, in this diagram, and you color the marbles based on the agreement and the disagreement of H2 with the ground truth target function. That's out of sample. In sample, your in-sample points, you have a level of agreement and disagreement. So you do that with H2, you do that with H3, H4, and so forth, up to and including some number M of hypotheses. And so you have many, big M, hypotheses that you search through, and you test each one against in-sample performance, nu, with the out-of-sample, mu. Okay? So we have this model with multiple bins, and this is exactly what happens with learning. You have sample sets, and you're looking for a good sample, and you're also looking for a quote-unquote good hypothesis, one that agrees to a larger degree with the ground truth target function, and then you stop when you get either enough different hypotheses that you can find one which is the best, and there's always a best, even if you have two of them, one is better than the other, and you look at how they perform on the same piece of data. Does that make sense? And so you have your data, you're searching through hypotheses, you're looking at the level of agreement and disagreement, and you find and return that hypothesis that gives you the best level of agreement. Okay? All right, any questions about this? No? All right. So we have our multiple hypotheses. And now we're going to kind of change the notation a little bit to kind of talk more about what happens in the anatomy of a learner in more practical type of situation. We said at the outset that the bin frequency for red marbles, we call that mu, and mu is hidden, but it's ground truth. And we said in the sample, we have the frequency of disagreement with between the hypothesis and the ground truth target function. We call that nu. So nu corresponds to error, right? Because if we count the frequency of red marbles, that corresponds to the hypothesis not agreeing with the ground truth target function. And because this is for in-sample points, those points that you sample from the bin, it's the historical data, we call that EN, or in standing for in-sample error. Now, in-sample error is parameterized by a hypothesis H because that error is going to be different depending on the hypothesis under consideration, right? The same training data for two different hypotheses will give you different error rates, right? Different types of agreement and disagreement between the ground truth target function and that particular hypothesis. So for that reason, in-sample error is parameterized by H, En of H, is going to be a replacement for nu, which in this scheme is the amount of disagreement between a particular working hypothesis and the ground truth target function. Does that make sense? Any questions? Yes. No, they're different. I haven't gotten to E out yet. No, thank you for bringing that up. All right, so likewise, we have the out of sample level measurement of disagreement, the proportion of red marbles, mu, right, out of sample, are the level of or the amount of disagreement or proportion of red marbles, they're all synonyms, between a particular hypothesis and the ground truth target function. And so we're going to replace that mu with E out, the out of sample error. Now, again, we said we colored a marble red if the hypothesis disagreed with the labeling of the target function. And so that is an error. A disagreement is an error. And because this deals with the out of sample points, all of those points across all the different feature values that are possible for all of your data, we call that E out, or out of sample error. And out of sample error is parameterized by the hypothesis because it's going to be different. So let's say you have all these feature values that are possible for your data points. And if you have a particular hypothesis, it'll disagree here, it'll agree there, it'll disagree here, agree, and so forth. If you change the hypothesis, all of a sudden, that agreement and disagreement is going to change. And so because those are out of sample points, we're going to replace this mu with out of sample error, E out, of a particular hypothesis. Does that make sense? And so to answer your question, En and E out are not the same thing. En traffics in the error for the in-sample data, and E out corresponds to the error for the out of sample error, out of sample points. Now, of course, these out of sample points, this is all theoretical, right? But we still need to be able to talk about it. And it's theoretical because here we're depicting all of the possible feature values that you can get and the disagreement or agreement between each hypothesis and all the possible instantiations that you can have for the data. The agreement or disagreement between the hypothesis and the ground truth target function. Does that make sense? Okay, so let's look at Hoeffding's inequality. We had our original expression for Hoeffding's inequality. We said probably approximately correct. So we said that the probability of the disagreement or divergence between your in-sample points and out of your in-sample points and out of sample points exceeds some error tolerance epsilon. That probability is at most 2e to the minus 2 epsilon squared n, right? So if we replace nu with En of h and we replace mu with E out of h, we get this expression. And what this says is that the in-sample error and the out-of-sample error will track with one another. They'll be close by one another within some epsilon, and that happens probabilistically. No more will it'll exceed that tolerance by no more than a certain probability. And that probability depends on both the tightness of the tolerance, epsilon squared term, as well as the amount of data, the sample size that you have. Does that make sense? Okay, so that's just a straight replacement, but we're not quite done yet. Okay, so we have our multiple bins, and now we'll replace this mu and nu with E out and E in. And we said at the outset, or a few slides ago, we have the first hypothesis, then the second one, and the third one, and the fourth one, and the nth one. And that's akin to what the learning algorithm does. It considers, in some sequence, a first hypothesis, a second hypothesis, a third hypothesis. And let's make the simplifying assumption at this juncture that we can visit every single hypothesis in our hypothesis set. So in that particular case, M, big M, since it's the number of hypotheses, M is going to describe the size of the hypothesis set. So you could have a small hypothesis set, maybe the degree 2 polynomials, or you can have a really large hypothesis set, the degree 10 polynomials. It's clear that the degree 10, it's so much larger than degree 2, it includes the degree 2 polynomials. Does that make sense? And so M, let's assume that we can visit all the possible hypotheses in the hypothesis set. And we consider each one in kind, the first one, the second one, the third one, and so forth, up to and including M, the mth one. And for each hypothesis, we can measure in-sample error for the first hypothesis. And then we have a theoretical out-of-sample error for the first hypothesis. And we can do that with each one of these hypotheses. Now, at the outset, we talked about this idea of Hoeffding's inequality. And Hoeffding's inequality, we consider a single hypothesis with a single bin and a single set of in-sample points and out-of-sample points, right? So we're going to combine these multiple bins using Hoeffding's inequality to get our ultimate result, right? So Hoeffding's inequality, it does not work for multiple bins. We have to do something different, and we kind of motivate that with the following example. So let's suppose you're going to flip a fair coin, right? And you flip this coin 3 times, and let's say, each of those 3 times it comes up heads, 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 right? Does that mean the coin is biased? What does that mean? Is the coin, did somebody do something to the coin to manipulate it if it comes up heads, heads, heads? You just got unlucky, right? Maybe if you flipped it 3 more times, it would come up tails, 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 and you'd say, it's 50-50, right? So let's say if you tossed a fair coin 10 times, right? The probability of getting 10 heads is very, very small, right? It's about 1/1000th. It's really 0.0009 something, right? So we'll round it up to 1/1000th. So you get that by taking your probability of heads, right, and you exponentiate it 10 many times, and you get something that rounds up to 1/1000th, right? That's a very rare event, or relatively rare. But let's take that experiment, and we'll do something that looks a lot like having multiple bins, right? We take 1,000 fair coins, right? If you can hold 1,000 coins, let's say theoretically you could hold 1,000 coins, and you take each one of these 1,000 fair coins and you flip them 10 times each, right? Now, if you do that, well, the probability that some coin out of the 1,000, when you flip each 10 times, is going to come up with 10 heads in 10 flips, right? And the reason for that, and it's a much more likely to have that happen, the reason for that has to do with if you do something enough times, you're likely to see some event occur, right? Because it effectively, if you think of this case in taking the 1,000 coins and flipping each of them 10 times, you're kind of exploring 10,000 different ways of doing it, right? And so as you increase the number of times you do something, you're exploring different parts of a space at the same time, and you're more likely to get even a rare event that occurs, okay? All right, any questions about this? That makes sense? So that's just a plain probabilistic argument, but let's relate this back to our system here for what learning looks like. And so you take your bin and you produce some samples for the first hypothesis. You produce some samples for the second hypothesis. You produce some samples for the third hypothesis. And if you do this enough times, guess what? You're going to get some sample for a hypothesis, the mth hypothesis or some other hypothesis, where you're going to get perfect agreement with your samples, right? It's going to happen. For the same reason, absolutely perfect agreement, it's a very rare event, right? Given what the red labeling proportions are in the corresponding bin, but it can happen. And if you do it enough times, that's going to happen. Even a rare event can occur. And that played out with our coin flipping example from the previous page, right? You could actually work out the math if you wanted to. It really is much more likely. Okay, so eventually the bad event happens. And so if you have to deal with this properly, Herfting's inequality falls apart if you're talking about multiple bins, but it works fine with a single bin. So what do you do? Okay, well, what you can do is you can say, okay, well, let me make the assumption that each one of these bad events, Herfting corresponding to a single bin, that violation of the error tolerance epsilon, right, I treat them as if they're non-overlapping events. Now, if we think about what happens in a Venn diagram, if you have a probability, a bunch of events in the Venn diagram, and I'm just going to draw out the events as circles. If these events do not overlap, the probability of any one of these events occurring is the sum of the individual events, right? And so that's the worst case, right? What is typical is that some of these events will overlap. Now, if these events overlap, well, that's not the worst case because this set of events is common to these two, and it ends up being smaller in probability, right? Because you have to subtract out the double counted overlap region when you put these probabilities of these overlapping events together. So in the worst case, you treat these individual events as if they are non-overlapping, they're independent, and you can just add them together, and that's going to give you the worst case for that probability. So in this expression, we have something that looks like Herfting's inequality, is exactly Herfting's inequality, but you notice here, it's En of G, not En of H. Now G, as we said when we talked about the anatomy of a learner, G was the so-called final best hypothesis. And G is the result of searching through some set of hypotheses, and it's the hypothesis that gave you the best coincidence with the ground truth target function. So how do you get to this final best hypothesis? Well, you try the first hypothesis, you try the second hypothesis, you try the third hypothesis, and you keep going and going and going until you try the nth hypothesis. And for each hypothesis, you draw a sample and you measure the coincidence in sample, E in of that hypothesis, relative to E out of the hypothesis. This is a single bin and a single instance of Herfting's inequality. So because each of these expressions, they violate this error tolerance, is bounded by a probability, you're essentially adding together the bound of this one for Herfting with the bound of the second one for Herfting, the bound of the third one for Herfting, and you're adding the bound for the last one for Herfting, right? So what you get here is you have the sum for the hypothesis M here, goes from 1 to big M, of the probability that in-sample error of the little mth hypothesis diverges from the out-of-sample by more than epsilon. Now, of course, from the single bin version of Herfting's inequality, we know that this expression underneath the summation is bounded from above by that e to the minus 2 epsilon squared n. So we can replace this expression here inside the summation with that bound, and we know that we preserve that less than equal to inequality. Does that make sense? Okay, so let's do that. And when we do that sum, well, we get the following sum. So we're replacing this expression here underneath the summation with 2e to the minus 2 epsilon squared n. And so we're summing this thing with itself, big M, many times. And so we end up with m times 2e to the minus 2 epsilon squared n. Does that make sense? And so this essentially says, let's take the single bin case, which applies for Herfting's inequality, that expresses the relationship between in-sample error and out-of-sample error, this PAC model, probably approximately correct, and it bounds it and says, if I have my conditions right, I know that my out-of-sample performance isn't going to be too far away from my in-sample performance. Okay? Now, I do this with multiple bins, and I make the worst case assumption that I don't know which hypothesis is going to be the best hypothesis, but if I treat them as being independent from one another, the worst it can be is the sum of all of these, right? So I do that, and this is my expression, 2me to the minus 2 epsilon squared n. Now, this big M, we said that M is the count, the set size, if you will, of the hypothesis set. If you have a more complex hypothesis set, M is much bigger. If you have a more simple hypothesis set, then M is much smaller. And so to kind of bring this all home with something that ties it together as it pertains to the anatomy of a learner, when we introduce the learning algorithm, we search through the set of hypotheses for that final best hypothesis. How we pay for that in terms of setting the right context for learning to be feasible is with this M term, and M is the complexity of the hypothesis set. A more complex hypothesis set takes longer to search, right? And so if your hypothesis set is too complex, what happens? Well, this complexity, M, for the hypothesis set, or the size of the hypothesis set, it sort of kills the dampening effect of this negative exponent, right? If your hypothesis set has many millions of different hypotheses, or if it's uncountably infinite, well, no amount of large sample size is going to decay this M to the point where the probability on the right-hand side of the inequality is going to be small, right? And so you could have a situation where you say the probability that E in diverges from E out by more than your tolerance is something that basically says it's going to happen all the time. It's going to diverge all the time. It's going to be really far away all the time. And what you want, in addition to having enough samples to pay for the error tolerance, you also don't want your model to be too complex. If it's too complex, we'll learn later in the semester, it does something called overfitting. And what this overfitting says is that your model is so complex, it doesn't learn how to generalize well. It doesn't perform well out of sample. It's essentially memorizing the particular sample that you have in sample. And so, of course, if we take a look at the bin, at what happens, well, when you have one of these bins, let's just consider the bin itself, right? When you have one of the bins and you produce a sample, well, the next time you sample, you're going to get different regions of feature space represented from the first sample. And so if your model is so complex, your hypothesis set so complex, it's basically going to learn how to categorize, and it's going to learn something about that sample, but only that sample, the details of that sample, and not the general geometry, if you will, of the labels as it pertains to the out-of-sample performance. And so through Hoeffding's inequality modified using something called the union bound, and this is what we have done, we use the union bound to talk about the multiple bin case, which is how we express this idea of the learning algorithm searching through the set of hypotheses for that final best hypothesis. And because it's a worst case, we assume each hypothesis that's governed by an instance of Hoeffding's inequality is non-overlapping. We get this worst case behavior. Does that make sense? Any questions about this? No questions? All right. So if the sample tracks out of sample, then larger sophistication, a more sophisticated model, will cause us to lose track, meaning that your in-sample performance is going to diverge very widely from your out-of-sample performance. And so not only do you not make your tolerance epsilon too strict, you also don't want your model to be too complex. And if your model is too complex, you're going to overfit. And it's very likely that your in-sample performance is not going to be representative of your out-of-sample performance. Now, of course, there are some mechanisms, in particular, one's called regularization, that we'll learn about, which is an automated method in a learning algorithm to force your model to prefer simple hypotheses instead of complex hypotheses. But at this juncture in the semester, I want to give the overarching framework using Hoeffding's inequality and the union bound to talk about the factors and the relationship between these factors that can impact your out-of-sample performance. Because at the end of the day, what we care about is not so much that your model performs well on the training data. What we care about is how your model will perform when you give it brand new data, i.e. the out-of-sample performance. Okay. Any questions about this? Final questions? That makes sense? So I really think it's a beautiful thing. Hopefully, you come to appreciate it too. Um, but with that, it is time. I think I'm a minute over. I'll end there, and I look forward to your submissions for the assignment, and I will see you all on Thursday. Okay.